Well, hello and welcome again to our journey into number theory, and we were looking at the prime number theorem, and we're going to just do a little bit here on the logarithmic integral. So this prime number theorem, of course, tells us that pi of x is asymptotic to x on log x, and although these two are asymptotic, it doesn't really give us a particularly good approximation to the actual value of pi of x. Gauss, of course, always had clever ideas, and Gauss suggested you might take an average, and so you average out by dividing by x and integrating. So he looked at this integral, which is known as the logarithmic integral, and sometimes written as Li of x. And the following table shows that Gauss certainly had the right idea. I've rounded them to the nearest integer in the table. So here's some values of n up to 10 million. Here are the values of pi of n, the exact values of pi of n. This is n on log n, and you can see that although the ratio is getting small, the actual numbers are not terribly close. On the other hand, if you numerically calculate Li of n for each of these values, then you can see it's pretty close. Even for 10,000, we're only out by a very small number. Even when you get up to 10 million, you're still only out by a relatively small amount. So in this little section, I'm going to show that Li of x is in fact also asymptotic to x on log x, and so it's asymptotic to pi of x. You can do a little integration by parts on this logarithmic integral, and if you do an integration by parts, you end up with getting x on log x minus 2 on log x plus the integral of 1 on log of t squared. So what I've done there is I've differentiated the 1 on log t, and I've integrated 1 to get the integration by parts. This suggests a couple of things. Firstly, that it might be easier to replace the 2 in the logarithmic integral by e. That'll make the constants appear a little bit easier. And secondly, one should perhaps, you can see how you could continue the process. You might look at families of integrals. I sub n of x is the integral from e up to x of 1 on log t to the n dt. And again, we do a simple integration by parts. Now that we've got a nice e here, it makes life a bit easier. We end up with x on log x to the n minus e plus n times I sub n plus 1, which gives me a nice recurrence relation. And indeed, you can keep repeating the process in a little tutorial exercise to show that Li of x then is just x on log x plus x on log of x squared, plus the general term is n minus 1 factorial x on log x to the n, and there's a remainder term, and you get the remainder term fairly easily to be asymptotically that as x goes to infinity. Now, little lemma here, as x goes to infinity, this I sub n, this family of integrals that we've defined, is asymptotic to x on log x to the n. So, using the above recurrence, one can show that this is equivalent to I sub n plus 1x, and multiplied by log x on divided by x, and you want this to go to 0 as x goes to infinity. Now we can split up the interval from e up to x into two sub-intervals. We've done this before, where you just go up to root x and then go from root x to x. It's a useful trick in many cases. So I'm going to write this as the union of two sets. So if I take any t in this first set, then the log of t has to be bigger than 1. And if I take any t in this set, then the log of t has to be bigger than the log of this, which is a half log x. So I can use these two different approximations when I split this integral up into two. So split the integral now from e up to root x and from root x to x. And I can use this fact that log of t is bigger than 1 if I'm on this interval, so I can just replace all this with a 1 with less or equal to. And similarly for this bit, I can replace the log t with this in the denominator, so this is less than 2 on log x to the n plus 1. This I can integrate, it's trivial. This one now is independent of t, so I can just take the endpoints and multiply that by this expression. And let me just toss away a few bits and pieces here. The root x, I can keep the root x. I'm going to toss away the e, and I'm going to toss away this root x. And so I get this is less or equal to x plus x times this quantity. Hence, if I look at I sub n plus 1 log of x to the n on x, then using what we've got here, this just simplifies down to this, and that clearly goes to 0 as x goes to infinity. Now, armed with that, we can prove that finally then that this lie of x is in fact asymptotic to x on log x as x goes to infinity, or more precisely that lie of x is x on log x plus a remainder, where this remainder term is asymptotic to x on log of x squared as x goes to infinity. Now it suffices to prove the equivalent statement I1 instead of lie of x, where we've just replaced the 2 with an e, and so I'm going to work with I1. So I1, using the recurrence we had before, I1 of x is x on log x plus I2 minus e, and by the lemma this I2 minus e is roughly x on log of x squared as x goes to infinity, and then the result clearly follows. So that gives me the fact that this lie of x is asymptotic to x on log x, and hence pi of x, but as you saw from the table, it's somewhat more accurate. There are many deep connections between lie of x and pi of x. For example, it was proven a long time ago that pi of x might, if you ask what's the difference between pi of x and lie of x, then this is less than some constant times x e to the minus c log of x to the half, where k and c are constants. So that's giving us a bound on the difference between the two. This result has not been bettered, but it is known that the statement that pi x minus lie x is root x log x is equivalent, in fact, to the Riemann hypothesis. So the nature of the zeros of the zeta function in the critical strip impose some sort of limitation on the accuracy with which lie of x can represent pi of x. Riemann and others believed that pi of x was always less or equal to lie of x for all x. And indeed, if you look at the tables that were calculated, ones we just saw, that looks reasonable supposition. This, of course, was proven to be false. And in fact, the two curves cross infinitely often, which came as a great surprise. That was done by Littlewood. The smallest x at which the curves cross is known as Skew's number, but it's not explicitly known. Its size was given initially by Skew's in 1933, was shown to be less than e to the e to the e to the 79, which is about 10 to the 10 to the 10 to the 34, which is somewhat large. The Skew's number has since been reduced to this 1.65 be 10 to the 1165 by Lemma in 1966, was further reduced to e to the 27 on 4, which is about that number, in 1987 by Terrielli, and then it was further reduced down to this number. We're getting down to only 10 to the 316 by Bay and Hudson in 2000. And the most recent work that I'm aware of by de Michel establishes that the crossover occurs around about this number. So this is getting pretty close now, 1.397, etc. by 10 to the 316. So we've come down from the astronomical down to the merely ginormous. And that's the end of what I wanted to do on the prime number theorem. And I'm going to just give a quick sketch proof of Neumann's proof, which I'll just pop in here, and I'll just give a little sketch proof of this. This proof was given in 1980 by Newman. It uses the equivalence of the prime number theorem to this. Remember, we proved that if the prime number theorem is equivalent to saying theta of x on x goes to 1 as x goes to infinity, in the proof we gave earlier we worked with psi, and this proof works with theta. The Wiener-Ikehara theorem that we used is replaced by the so-called analytic theorem, which has the advantage that it can be proven, which I'm not going to give a proof of here, but it can be proven using only a simple contour integral, and you can look at Newman's proof of that. So just as an outline proof, we start off with this capital phi of s, which is the sum over the primes of log p on p to the s. And the first little theorem here is that phi of s minus 1 on s minus 1 is holomorphic for the real part of s bigger or equal to 1. So the proof of this is simply if s is real and s is bigger than 1, then it's an exercise to prove that the minus the logarithmic derivative of zeta can be written as the sum over primes log p on p to the s minus 1. The right hand side of this is also equal to, just rearranging this is phi of s plus this sum. This latter sum converges for s bigger than 1, which is easy to show, and so by analytic continuation it converges for complex s provided real parts bigger than a half. Since this has a simple pole at s equals 1 with residue 1, the result follows, because I can just subtract off the principal part of that function and I'll have an analytic function. So it's holomorphic for the real part of s bigger than 1. Now the so-called analytic theorem, which Newman developed, he used this one in place of the Wiener-Ikehara theorem. It says that if f of t is a bounded integrable function, and we look at this transform here, g of z is the integral of f of t e to the minus zt dt from 0 to infinity. For the real part of z bigger than 0, then if that extends holomorphically for the real part of z bigger than 0, then this improper integral converges and is equal to g of 0. And this, of course, is just the Laplace transform of f, so he's simply taken g to be the Laplace transform here. And he calls this one the analytic theorem. So Theorem 3 then is where the hard bit of it comes. This integral of theta of x minus x on x squared, as you go from 1 to infinity, this integral converges. So the idea of this, again, we take b of n to be 1 if n is a prime and 0 otherwise, so this b is just a prime counter again, we've seen these before, and theta of x then is just going to be, can be written like this, because remember theta of x was log of the sum of the log of the primes less or equal to x, and if bn is it simply picks out the primes giving a 1, then clearly these are equal. And this phi of s, which we defined above, I can now write using a sum over, rather than working with a sum over n, a p, I can work with a sum over n using this bn. So for s real and bigger than 1, the theta of x on x to the s is less than x log x on x to the x as x goes, this goes to, sorry, is less than this. That's by what we've had before, and that goes to 0 as x goes to infinity. And again, we can use Arbel's lemma with an to be b in log n. The sum of that's going to be, partial sums are going to be theta of x, and we take our function to be 1 over n to the s, and we apply Arbel's lemma. We put x equals e to the t, and we can write this phi of s that we introduced before, which was defined to be this. We can now show that that's equal to the limit of theta of x on x to the s plus this integral. So I'm just using Arbel's lemma or Arbel's identity here, and this one we can write as s 0 to infinity e to the minus st theta of e to the t. There I've simply put x equals e to the t in there. So putting f of t equals to this, so I want to be able to use this analytic theorem, so put f of t to be this and g of z to be this expression. Then the conditions of theorem 2 are satisfied, and so this integral exists, and if we replace e to the t with x, we arrive at the appropriate integral that we had up here, and that means this thing here converges. Finally, we want to show that theta of x is asymptotic to x, which is the equivalent to the prime number theorem. So again, we suppose lambda is bigger than 1, and there exists arbitrarily large x so that theta of x is bigger or equal to lambda of x, and we want to get a contradiction out of that. So for t bigger than x, we can write theta of t is bigger than theta of x, which by our assumption is bigger than lambda x. So this integral from x up to lambda x of theta t minus t on t squared is bigger than, we can replace the theta of t bigger than lambda x, and we can make a change of variable here. We're just rescaling back by x, and we get this integral, and this one comes out to be this quantity here. So lambda plus 1 minus log lambda is positive. Here I put u equals t over x. That means the tail of the integral is not going to 0, but this implies that the improper integral diverges, and that contradicts our theorem 3. So similarly, if the inequality theta x is less or equal to lambda x with lambda less than 1 would imply that this integral is negative, and that again contradicts theorem 3, and so we can conclude that theta of x is asymptotic to x, and that the prime number theorem follows from that. So that's just a quick sketch proof. You can work through all the details later. That was given by Newman, and it's probably the easiest proof we have of the prime number theorem.